Where is my window? Hold on. Okay, okay, so if you recall last class, we discussed support vector machines, and it's for classification. So the theory behind SVM. And the major point is to try to find the hyperplane that can maximize the margin between two classes. Okay, so that's the major information for SVM. So today, let's take a look at the examples. So the first example, if you recall previously, for the example, we discussed the RS flower classification. So we're going to continue using the data from the RS flower data set. But this time we are going to do support vector machine classification. Okay, so to do the SVM for sklearn, then we import, it's called SVC. Okay, so just keep that in mind. In sklearn, the SVM model is called SVC. Okay, so if we want to use that, then you create the support vector machines object. And here, if you recall the kernel, because initially when we discuss SVM, etc., it's for linear. It's for linear, but then we expand it, etc. So we can like add some more high order terms, etc., and then project to high dimension. Project to high dimension, then we can use kernel concept, etc. And there are a number of kernel functions. So over here, so this kernel, so this goes to linear. Okay, goes to linear. And C, we already know, is that this is for regularization. Okay, just as previously discussed. Okay, so the model is created. Okay, it's created, and then you fit the model. That you fit the model. So over here, we also borrow the previously discussed function to do the plotting, so that we can have some idea. Okay. So here is plotting. So over here, we consider 3 classes. Okay, so if we use the S from sklearn, we don't need to worry about just binary. Okay, it will take care of that. So after we train, then we can do the predict and the plug in with testing data. Okay, and here we also collect the accuracy score. So we can see it's pretty high. It's almost 98%. So we can see if we want to use like the model from sklearn, it's not too complicated. Okay, in this case. So a lot of part is you need to do the data cleaning. Then after you have the data cleaned and pre-processed, that then we can create a model and fit. Okay. And And then, so here is some alternatives in sklearn. And if you recall, so this is stochastic gradient descent. Okay, stochastic, and the previous discuss is not a stochastic gradient descent. So with the, so it's batch processing. The batch processing is including all samples at a time. Okay, and stochastic gradient descent, then it's just one at a time, one sample at a time. Okay, so it for the batch one, then if your data set is too large, is it they cannot all fit into memory? Is it they cannot all fit into memory? So that can cause some issues. So we need to do one at a time. That's a stochastic gradient descent. Okay. Okay. With stochastic gradient descent, it's a linear model, and you can pick a different one like the perceptron. You can also apply with stochastic gradient descent. With the classify, what you choose here, the perceptron, is it? And here the loss basically is regarding the cost function, the concept. Okay, so you said, okay, I'm going to pick for the perceptron model. If you want to do logistic, then the loss, you see, okay, this is for logistic regression. And if you recall previously when we discussed the linear support vector machine SVM, its loss function, what we pick is we call it a hinge loss. If you recall, as it previously we discussed, so it has either 0, so that means predict correct. If you predict correct, of course, the cost is 0. Is it? Otherwise, it's 1 minus something. Is it? So predict wrong. So that's the hinge loss. Okay, hinge. So if you said, okay, the loss parameter is a hinge loss function, then this means you're going to do the SVM, okay? So with this SVM, then we can also do train, is it? And the same thing, we do some plotting so that we can find, we can view it clearly about the decision regions, is it like in this case, 3 regions. And then we can do predict, okay? And we can also do accuracy, okay? And over here, we fit the model, etc. And then this time it's with the perceptron. Then you can also do predict and accuracy score. And the next one is for logistic regression, etc. So if you want, you can also just use the stochastic gradient descent, and then you select a different model for the training, is it? Then you can do the comparison. So here so looks like in this case, the difference is not, there is almost no difference regarding the accuracy. It's all about 98%-ish, okay? And what the next one try to show is about nonlinear, because some cases, if you recall, like what we see, like if the data distribution is something like this, is it? Then this is a class, linearly you cannot separate, is it? But if we project them into 3-dimensional, is it? Into 3-dimension, then it's separable. Separatable, is it? So let's take a look at the example, okay? And here for the data, we just use some random generated data, okay? So this part's not, it's all about, we generated some data, okay, including the features. So it's all numeric data. So here is our data set. So this data set clearly, you can clearly see if we use linear separation, it's very hard, is it? And then let's see if we choose kernel, is it? So we support vector machine SVM, is it? And the kernel, this time it's not linear, is it? This is the RBF one. That's the most common one, okay? And for this one, and because for nonlinear, if you recall, it also has some parameter called lambda, okay, going to impact the kernel function. So we also need it. So besides, you consider regularization. So this is for regularization. The regularization, if you recall, generally, so L2, previous we discussed is L2 regularization. The regularization, then generally speaking, it can prevent overfitting. Because this is kind of, you add more impact from bias, is it? And we know if you have too high a bias, is it will kind of cause what? Underfitting. But for overfitting, if you try to, then you can manually add some bias, is it? So that's regarding the regularization term. And this, the gamma is in the kernel function. So it also has the role, okay? So we will see later on the discussion about the gamma. Previously, we saw that C, is it the C? Okay, so this is the model we created, is it? And then we fit the model, and this is the plotting. So we can see with the linear, with the kernel ones, is it? Then it's kind of, we can separate these two classes, is it? Okay, then it's regarding that parameter here. We will see more, okay. So the parameter, if you read the documentation regarding the SVM, so the SVC model from the official documentation, it will give you detailed explanation, okay, about all of the parameters, okay. So the gamma parameter is that it can be understood as some cutoff for the Gaussian sphere, if you recall previously. As is a simple case, is that, and then we can project into 3 dimensions, is it? So the Gaussian sphere, is it? It says if we increase the value for gamma, is it? Then we increase the influence of the training samples, okay? Then it can lead to tighter and bumpy decision boundary. We will see that, okay, we will see that. So anyway, so here we have this previous one, the gamma is 0.1, is it? So we can see it's kind of generalized pretty well. And now we increase to 0.2, is it? And for 0.2, then you can see the decision boundary changed. Is it? It's still quite smooth. Is it? Not too bad, is it? And then let's see, the next one, the third one, we increase gamma to quite a large value, 100. Is it 100? And then we fit the model, then we plot. And if you take a look, then it's like the previous explained. Is it the decision boundary? Is it between two classes is quite tighter? Is it when we use large gamma values? Is it it's tighter? Is it it's tighter? It's tighter here, is it? And it's tighter basically, then it will not generalize well. Okay, it will generalize well for more new data. Is it new data? Then this can cause what? Cause overfitting issue. Oh, sorry. Oh, hold on. Okay. Can you still see my screen?
Yes.
Okay, hold on.
Yep.
For some reason. Oh, okay. Let me bring it back because a lot of there are so many emails coming, and then it's just automatically popped up and over my screen. Hold on, let me get back. Where is my, where is that? Okay. So you can you still see my screen?
Now we can.
You cannot?
And now we can, yes.
Oh, you can see, okay, sorry. Okay, so
Actually, I have a question.
Yes.
Could you explain what is gamma again?
Okay.
What it stands for?
Okay, the gamma, okay, then I need to find the slides. I haven't bring up my slide. Can you hold on? Okay. Let me first find that slides. Hold on, hopefully I still have that slides. Okay. Hold on, okay, let me find that page. Share screen this time, it's this one. If you recall, is it in the theoretical part we discussed, is it whenever you try to solve non-linear, is it then we use the kernel concept, is it? So basically, is the original it's 2D, is it a feature? Then it's kind of you bring it to 3D features. With this 3D feature, then definitely you can separate that. Is it because the other one we bring up is x1 squared plus x2 squared? Is it? So this can be considered as the third. So Z1 is still map x1, Z2 map x2, then Z3 the map x1 plus x2. So it's kind of you increase the dimension, that you add more feature, etc. Okay, so that's the nonlinear, the general idea. But how do we find the high dimensional space? Is it so? The concept is find the kernel function. Is it the kernel function? So the kernel function. So here, if you just use the like do some one kind of function do that conversion, then it's a little bit of, it's quite expensive, okay, quite expensive with so many data. So that's why then we create some, we call it a kernel function, then it can map this, okay. And so behind this, it's a lot of advanced math problems, okay. So the experts already like find out a number of quite useful kernel functions, okay. Like the one RBF that we just saw in our SVC model, etc. So that one is one of the widely used kernel, okay? And it's also called Gaussian kernel, the Gaussian kernel. So the Gaussian kernel, basically it's exponential, is it exponential? And here is the variance, is it variance? Okay, and then we can rewrite it as using gamma. So this is that gamma. So that's how, where the gamma come from. Okay, does this make sense now? This gamma is basically, it's from the original kernel function, okay.
Okay, I think it makes sense.
Okay, yes, then let's get back to where is my, okay, this. Now let's get back to this one. As this one, in this example, that the SV, because it's non-linear this time, is that we use that RBF, is that. So for RBF, then you need to pick gamma, is it? So this all regarding a hyperparameter tuning. So when you do machine learning, so it's not you just plug in the model, is it? So there are also quite a lot of job is you also need to find the best, the optimal parameter, is it? So the regularization we already discussed, is it? And the gamma is another one in this case for nonlinear kernel, okay? And initially it's start at 0.1, is it? And for this case, it's quite good, we can see, is it? Then we just try to say, okay, if we increase, is it? Yeah, it's not bad, is it? And if we increase more, of course, it's quite precise. So more precise prediction on training data with larger gamma. Is it? You can see it because it's so decisive. Is it? So it's good on training data. Doesn't mean it's going to be good for new incoming data. Is it? So that's why we see this can cause overfitting. So in machine learning, we need to balance well between overfitting and underfitting. Underfitting, is it? And previously we discussed like variance, is it, versus bias, is it? So high variance can introduce the overfitting, is it? High bias can introduce underfitting, is it? So for nonlinear, the gamma parameter also plays a role. So that's why when you do the model training, you need to train in different scenarios, that then you try to find the optimal one, okay? Okay, so for this iris one, we SVM, so that's covered. Next one, let's take a look more regarding the stochastic gradient descent. Okay, so this is another example. So on our website, it's called ML Logistic Regression version 2. Okay, find that notebook example. Anyway, of the previous part, I borrowed from the most famous one, okay, for machine learning class, okay. But what his class cover doesn't use sklearn Python part, okay, because that's a number of years ago, okay. So use the Octer, I believe. But his example, there are some other researchers already converted them to Python, so I borrow them here. Okay, so anyway, so all of this just shows some data. Okay, so not a big deal for us. So anyway, just some data, and then use do splitting, is it do data pre-processing, data scaling. Don't forget this part, okay, when you do your assignment and exam. And it depends, okay, it's not always you need to do data scaling, but if your features, the scaling, is it offset a lot, then you need to consider the data scaling. And the stochastic gradient descent is a detailed explanation. And if you wanted to investigate more, you can go ahead and read the official documentation. Okay, there are more discussion. So gradient descent is just like I previously explained. So the gradient of the loss, so the cost basically. So here loss cost is what we previously mentioned as a cost. So it's estimated each sample at a time. Okay, and then the model is updated along the way with a decreasing strength schedule. Okay, so that's for stochastic gradient descent. Stochastic gradient descent, but of course, it also allows mini batch. Okay, so here be careful. We have the concept about pure batch. Pure batch is all samples. Okay, then you have mini batch. Is it? So mini batch is you can further split your data into some small batch, is it? And pure one at a time, is it? So stochastic gradient descent also allows mini batch, okay? Because if the data size is too huge and you just do one by one, that's also not efficient, is it, for convergence, okay? So for stochastic gradient descent, previously we already discussed, you can use like logistic regression. Okay, so this represents logistic. And over here, it's just a review, as it previously, if you recall, for performance. For performance matrix, is it? It's not just accuracy, okay? We can also use confusion matrix, okay? Using confusion matrix to add more analysis. Okay, and with the confusion matrix, is it, then we can also have more report. So if you want, you can get the matrix from classification report, is it? That give you classic precision, recall, F1 score, is it, etc. Okay, and the score, okay. So those parts we already learned, so there's not a lot of new things. What the next part try to show is with stochastic gradient descent, we can also improve from first order to some high order terms. Is it? So not just for SVM, you can, for nonlinear, is that you can increase. For other, you can also, so previously, basically, we also discussed, is it with polynomial? Is it? And the polynomial, then you can have high order term. Higher order term, okay. So then what this one is a hard coded, okay, and we can skip because you can clearly see, is it? So here it's initially just have 2 exams, then you can add features, square, is it? Square the exams, then the term, the feature changes to 4 feature from the original 2 feature, is it? You can also add the cross relationship between exam 1 and exam 2, is it? Okay, and for from sklearn, is it? It also has the polynomial feature that we can borrow, is it? So then if you set it to 2, then it will create a feature up to 2 degrees, is it? Then in this case, then you will have more features, kind of, is it? And with this one, is it? Then of course you need to do the fit transform, is it? And with the logistic regression from sklearn, is it? We can also plug in with the polynomial data, okay, increase data. So over here, if you see, is it over here, we can also plug in with the higher order terms, okay. And so that's so basically an idea is if you try with linear first and doesn't the result is not too good, then you can consider to see if polynomial ones is going to be good or not, as it can improve the efficiency, okay. So that's regarding the second example. Okay, for the third one, the support vector machine SVM part, it's not, there's nothing new, okay, based on what we saw previous examples over here, okay. So nothing new, so just some new sample data and then do the training, is it? Okay, so, and with a nonlinear model, is it? Okay, so that's not, so that part, not a lot of new thing. So hyperparameter tuning, is it, in our previous example, we also discussed, is it? So just keep that in mind. The gamma, of course, this is for SVM, is it? It's for nonlinear, okay, for nonlinear. Normally, it's lower value of gamma create loose fit, is it? And the high value one will create model get fit more appropriately, is it? But it may also lead to overfitting, okay? So that's, and this C is for regularization, is it? And for regularization, and be careful, okay, C is, if you recall, it's the inverse of that lambda, is it? And that lambda is is regarding the weight for the L2, is it? So C is the inverse of it, is it? So if this is smaller, then this is larger. This is larger than this impact is more, is it? So it will bring down more to underfitting side, is it? And if we increase this, is it? That may lead to overfitting because it's decrease the impact of this L2 term, okay? So this is regarding hyperparameter tuning. And what the next part to try to show is, as we will show the with different different C and gamma values. Okay, then let's see what's its impact. So we will use the SVC model. Okay. So for this one, yeah, so over here, the values is different C gamma, is it? And then for the SVC model, is it? And what over here is, it's pick the best one, okay? I pick the best one, and we can see its result is not too bad, okay? So that's regarding the tuning of the parameters. What is the next one I'm trying to explain? It's also interesting, okay? Interesting is, if you recall previously, we already kind of see MNIST data set. Is it MNIST data set? MNIST data set is regarding kind of image recognition. Is it image recognition? So very, very basic one, is it? And what today we will see another example is about spam classification, okay? And for image, basically, you convert the pixel values, is it? So each pixel will be counted as a feature, is it? For the spam, it's all word. Is it like email, like text message? Is it like those? They are all word, is it? So how are we going to deal with word? Because for machine learning, you need numeric data value for training, is it? Because it's, if you recall gradient descent, is that it's all math, it's need a numeric value. So how are we going to handle that? So here we have some email samples, and over here we also have another one, we call it vocabulary library kind of, okay. So first let's take a look. I have those two data, yeah. Let's first take a look at the email. So this is one of the emails. So we all know it's a plain text file. Okay, so here we just consider plain text. And then next, let's see the vocabulary. Okay, this is a vocabulary. Okay, for the vocabulary one, if you take a look, so for each vocabulary, is it matches a numeric number. Is it? It matches a numeric number. Okay, so that's what this vocabulary list. Okay, then let's get back to our example. Okay, so anyway, so first we have those two files, is it? And with the email, with the vocabulary, and for the vocabulary, what we are going to do is it's line by line. So we need to deal with, we need to extract each word out, is it? And we are going to put it in a new dictionary. So the previous arrangement is numeric value, is it, then word. So now with the dictionary, as we want a key has the word, is it, and then the number, is it be the value. That's what we are going to create. So what we are going to have the keys and the values, is it? Okay, so this is the email. So that's just a plain text part. Okay, then what next we needed to do is with the spam classification, is it? So there are so many words, and a lot of words, they have the same stem, is it? So there's a term called stemming involved. Okay, so stemming is as a process of producing morphological variants of a root or base word. Is a base word. So it's that some algorithm is going to reduce the word, like all those chocolate related with the word chocolate. Is it retrieval, retrieve, reduce to retrieve? Okay. So anyway, so here they are going to use the stemming. Okay. And the stemming is that it's used a lot for information retrieval. Okay. Like a search engine. Okay. So this is involved another big field, okay, natural language processing, is it, and information retrieval, is it. So it determines domain vocabularies, domain analysis, okay. So we just take a glimpse of how that works. So anyway, so for the email, what it's going to do is the email contents. So that's what this method. So that's the email file, and this is our dictionary for the vocabulary. Okay, so that's for this part. Okay, this part. So email contents. Okay, and we do some numeric number. Also handling, is it, to substitute the numeric number to number and substitute the HTTP with the HTTP address, substitute the email with email address, the $, and the replace of the special characters, is it, just remove them basically. And this port stem is from the library. Okay, it's not ours. Then for each of the email word, is it, we are going to do the stemming, is it? Because of our vocabulary list, it may just include those stemming words. So that's why we need to do this, okay? And then what next it shows, it's going to create a word indices list, okay, list. So what it does is for each of the email, suppose the email you have hello, then you have word. Okay, CS 453, machine learning. Is it? So all of this word in the vocabulary dictionary, they have the corresponding number. As I suppose this is 100, this may be 9,999. This may be a number like maybe 95. This may be a word, okay, 1,000. This may be a word, a number represent as 2,000. So anyway, each word has a number from the vocabulary list. Is it? That's what we are going to do, this word indices. So this word indices will have all of the email word be stored as a number. So basically you convert them to the number, numeric values. Okay, so then we see, is it, it's all number for the email, is it? So it's also kind of, you do some encryption, is it? Yeah. So then what next we are going to do is we are going to create a feature. The features, is it? So for a specific email, is it? We need to have the feature column, is it? A feature column, okay. So that's what this part is, okay. So regarding each word, is it? Then you will see, okay, if it is, if the word is in the email, appears in the email, then you assign it to 1, okay. So this is our feature list, okay. So once we have this, we have features, etc., and then we can do the training, okay, with our SVM model. And over here, in this example, the original data is from MATLAB. Okay, so it's not a plain text, so it's not readable. But anyway, they already, they can be dealt in our SVM model, okay. So anyway, we got the training data. We also got the classification, spam or not, is it? So that's the that's our top 5 samples, is it? So you can see it involves the feature. So this is the feature column. So it's quite large, is it? Because your vocabulary list is large, is it? There are a lot of 0, is it? And for each row, it's maybe 1 email something, is it? For the word to do the training, is it? So a lot of 0, that means the word not appear. And this is regarding if it is spam or not, is it? So you have quite a large data set, do the training, is it? And then we use our SVM. So here we do linear training, is it? Linear training. So no gamma, is it? And then we do the fit. And you can see the training accuracy is also pretty good. It's almost 99%, is it? And then it does the testing. And then for the testing, then the accuracy is also pretty nice. It's almost 99%. And then based on the available data, is it? It try to pick up the top predictors for a spam email, is it? For a spam email. So what over here it does, it's based on the weights. And how do we collect the weights? From the model that we already trained. If you collect its coefficient, is it? Then you will collect all of the weights, okay? Because each weight map each feature, is it? And you align, so the high weight then definitely means that specific word, in this case, will contribute more to spam. Is it to spam? So that's what this part. And then you just do the sort value, is it? And then we can pick the top words, top 15 words, and here it gave and the corresponding weight, as it appears in the spam. Okay. Okay, so that's all the information.